Good day! Now we will tackle about outcrops. What is outcrop? When weathering and erosion expose part of a rock layer or formation, an outcrop appears. An outcrop is the exposed rock, so named because the exposed rock crops out. Outcrops provide opportunities for field geologists to sample the local geology, photograph it, hold, touch, climb, hammer, map, sniff, lick, chew, and carry it home. Classes often visit outcrops to see illustration of the principles of geology that were introduced in lecture. You often can see geologists or students identifying rocks in road cuts, outcrops along the road where highway constructions expose the rocks, mountainous regions where any loosened earth material swiftly washes away contain some of the best outcrops because a greater percentage of the rock formation lies exposed. Rocks crop out especially well across steep slopes, above the tree line, elevation above which trees cannot grow, and on land scraped free of soil by bulldozer-like glaciers. Sediment collects and plants grow in flatter areas, obscuring the rocks. In some areas, soil and sediment may completely cover all the underlying rock, such as in the southeastern United States. However, in the desert southwest, the opposite is often the case. Outcrops cut the cost of mapping for geologists. The greater expense of geologic mapping in an outcrop-free area results from high-priced drilling to sample the rocks hidden below the surface. Study in outcrop. Many researchers who study about it in the outcrop that they become shared, such as researcher Hodgett's 2013, who did the title Laser Scanning and Digital Outcrop Geology in the Petroleum Industry. A review who says here systems for modeling petroleum reservoir analogs has become increasingly popular over the past few years, and there has been a proliferation of articles on the subject both on techniques and applications. A review of literature of recent years has been conducted focusing on the use of LiDAR data not only in the petroleum geology-related projects, but also looking to the wider fields of LiDAR usage to examine what other approaches may be of use to the petroleum geologists. Benefits of digital data acquisition are considered, as well as a basic overview of data collection approaches. Use of a variety of attributes, intensity, color, depth, azimuth, collinearity, coplanarity, among others, is discussed and are an aid to both manual and automated interpretation approaches. Integration of LiDAR data with other data types from traditional field data, sedimentary logs for example, and other digital types such as multispectral and hyperspectral imagery and ground-penetrating radar are discussed as a way of increasing the amount of information in the digital database set. The application of artificial intelligence approaches such as smart swarms and neural networks are considered, as well as current developments in both hardware and software. A variety of examples are given where LiDAR has been used in an innovative or interesting way, showing the strength of this data acquisition approach when combined with appropriate interpretation and modeling techniques. There are others here who says, like Jones, 2009, that his work is titled Integration of Regional to Outcrop Digital Data, 3D Visualization of Multi-Scale Geological Models. Shown here, multi-scale geological models contains three-dimensional spatially referenced data, typically spanning at least 6 orders of magnitude from outcrop to regional scale. A large number of different geological and geophysical data sources can be combined into a single model. Other than that, a lot of research has studied it like I saw in the internet already. Outcrops allow direct observation and sampling of the bedrock in situ for geologic analysis and creating geologic maps. In situ measurements are critical for proper analysis of geological history, and outcrops are therefore extremely important for understanding the geologic timescale of Earth history. Some of the types of information that cannot be obtained except from bedrock outcrops or by precise drilling and coring operations are structural geology for features orientations, like bedding planes, fold axis foliations, depositional features orientations, like paleocurrent directions, grading, facies changes, paleomagnetic orientations. Outcrops are also very important for understanding fossil assemblage, paleo-environment, and evolution as they provide a record of relative changes with geologic strata. Outcrop confidence level. Outcrop confidence is the relative measure of the predictability or homogeneity of the structural domain and lithology of the rock unit from one exposure to another or to the proposed site of investigation. The three levels of outcrop confidence are defined as Level 1, high. Rock units are massive and homogeneous, vertically and laterally extensive. Such geology has a history of low tectonic activity. Level 2, intermediate. Rock characteristics are generally predictable, but have expected lateral and vertical variability. Structural features produced by tectonic activity tend to be systematic in orientation and spacing. Level 3, low. Rock conditions are extremely variable because of complex depositional or structural history, mass movement, or buried topography. Significant and frequent lateral and vertical changes in rock units can be expected. Once a rock unit has been established, it can be defined by classification elements and analyzed for performance in relation to selected performance objectives. Geologic maps depict the location of different rock units and buildings in the surface of the Earth. Many of these systems engage with topography in predictable ways because they are planar or nearly planar elements. Flat-lying beds. Beds that are horizontal or almost horizontal are known as flat-lying beds. Their contacts must be horizontal as well, because contacts on maps are roughly parallel to contour lines. The different colors used to classify rock units are limited by contour lines and thereby accentuate the topography on geologic maps depicting flat-lying rocks. The photograph on the left shows a bird's eye view of some sub-horizontal rocks near the Grand Canyon. The map on the right depicts a section of the Grand Canyon. Even if they are from different locations, you should be able to see that the bedding to topography relationship is the same in both. It's worth noting that the geologic map's contacts run parallel to the contour lines. As a result, the various colors reinforce the map's topographic appearance. The rule of V's. The rule of V's, which says that when dipping surfaces are incised by stream valleys or canyons, their map view would render a V in the direction of dip, is one of the most significant generalities. Whether the surfaces are vertically dipping, they will not form a V. If they are horizontal, they will meet the contours, resulting in a V that points uphill. The beds in the picture slant to the left and toward the viewer. The outcrop pattern is such that the beds V in the way they dip wherever they are split by gillies. This is an example of the outcrop pattern, the rule of V's. The Mesoic rocks along the San Juan River, SE, Utah. Plunging folds. Plunging fold map patterns create zigzag patterns that shift directions at the fold hinges. Anticlines descend in the direction in which folds close, while synclines descend in the direction in which folds open. Take a look at the picture and map below. They're all from the same part of Montana in the southwest. Examples of outcrop. On Ordnance Survey maps in Great Britain, cliffs are distinguished from outcrops. Cliffs have a continuous line along the top edge with lines protruding down. Outcrops have a continuous line around each area of their rock. Here are some other examples of outcrops.